somewhat old story, but it'd be useful to review that because the last few years we've extended this story, and it's in many ways it's parallel. It's very analogous to this old story of the heterotic string. But the main topic, of course, is these extensions that have been done in the last few years. Okay, so before I do that, I have to give a very brief review of particle physics, because given audience, I don't know exactly what to assume. So, of course, what we know and love is the standard model, and this is a gauge theory. The gauge group is SU3 times SU2 times U1. We have 3 generations of matter, and then we think we have also a Higgs field, which completes the standard model and causes electroweak symmetry breaking. Now, the thing to note about, if you just purely look at the representation theory of this group and the matter representations, that at least modulo the Higgs, they fit very nicely with the group theory of certain simple groups. So SU3 times SU2 times U1 can be embedded in a simple group, which is SU5. That's the smallest simple group you can embed it in. And if you do that, then the matter representations, they just correspond to 3 generations of a 10, that's the antisymmetric of the SU5, and a 5 bar of the SU5. Okay. The Higgs doesn't quite fit, and this book always cause some problems with this idea. But at least as far as the matter representations goes, it fits very nicely in the representation of the simple group. You can further extend this by taking slightly larger groups, and it looks even more pretty, more unified. So SU5 can be embedded in SO10. And if you do that, then and you also add a right-handed neutrino, then a single generation of a 10 plus a 5 bar together with the right-handed neutrino fits into a spinor representation of SO10. So SO10, in some sense, unifies the matter representations together with the right-handed neutrinos. And you could go and try even further. And SO10, the next step is fitting SO10 into E6. And if I also add Higgses plus some additional particles, which you have to get rid of at some point, into the vector representation, SO10, then the matter and the Higgses fit together into the 27 of E6. So the 27 representation of E6 unifies the Higgses and the matter of the standard model. Now, this is just group theory. It looks suggestive, but there are some concrete hints, experimental hints that this idea of fitting these various gauge groups and matter representations into representations of a larger group, that this idea is on the right track. And the main evidence for this, one of the main evidence for the idea that everything fits into the simple group, is the idea of supersymmetric unification. So supersymmetry we need for certain other reasons, namely stabilizing the electroweak hierarchy. So if you then just take the known values of the couplings for SU1, SU2, U1, SU2, and SU3, add the supersymmetric spectrum, and then just do a simple one-loop computation and start running it up. It turns out that the 3 couplings meet to a rather amazing degree of accuracy at an energy scale of about 10 to the 16 GeV, which is only 2 orders of magnitude below the Planck scale.
That's actually the 2-loop running that people usually plot. But
You have to do corrections to this, threshold corrections and so on, but just the 1 loop already works amazingly well. So this is evidence for the fact that at high energy scales, around 10 to the 16 GeV, you have a single gauge group, a single force, which is maybe based on SU5 or SO10. And since it's a single group, it would have a single gauge coupling. So that's why these couplings all sort of have to approximately meet at this energy scale. And this single force is then broken to the 3 forces that we know and love at low energy scales. And as soon as it's broken, then these couplings can run independently. Okay, so this is the idea of grand unified models. The grand unified theory is the idea that you start with a single simple group at a high energy scale, which is then broken at lower energies. Okay, there's additional evidence for this idea, which I won't go into. Okay, it's been one of the major, it's certainly been a major driving force for ideas for physics, possible physics beyond the standard model. Now we would like to get this from string theory, and the first try that this was essentially succeeded was the old story of the heterotic string by Candelas, Horowitz, Strominger, and Witten. And the idea is that there is this 10-dimensional heterotic string theory with an E8 times E8 gauge group in 10 dimensions. And below the string scale, the low energy theory is just E8 times E8 10-dimensional supersymmetric Emil's theory coupled to n=1 supergravity. And okay, so that of course has way too much symmetry. We want just a 4-dimensional grand unified model. So now we're going to have to break the symmetries. So we break, first of all, we break the 10-dimensional Poincare symmetry to 4-dimensional super Poincare symmetry by compactifying. That is, we take your 10-dimensional space-time, we take it off the form to be R4 times some internal 6-dimensional manifold. And super Poincare variance actually requires that this is a Calabi-Yau threefold. And further, then we have E8 gauge groups, which are way too large, so we'll also want to break those symmetries. And the way we do that is by turning on a bundle, V, on this internal Calabi-Yau manifold. This breaks the symmetry, and so depending on the holonomy group of the bundle that you take, you break this E8 symmetry to a smaller group. And particularly, you can get SU5 in a very straightforward way. Okay, again, the n=1 super Poincare symmetry in 4 dimensions puts some constraint on this E8 bundle V that you put on your internal Calabi-Yau. So these are, of course, the well-known Hermitian Yang-Mills equations. Holomorphic coordinates, the 0,2 part of the curvature has to vanish, and the Hermitian trace of the curvature also has to vanish. So a vacuum, or a classical field configuration, is specified by a choice of a Calabi-Yau threefold and a bundle on it, satisfying the Hermitian Mills equations. And okay, once we have a vacuum, we want to know what's the low energy theory, what's the low energy effective theory, what's the content of massless particles. And supersymmetry is a lot of help here. So the massless fields you get from the KK reduction, you can show that, well, of course, the massless modes are zero energy eigenmodes of the Dirac operator, but the Dirac operator is just a Dolbeault operator, and in this context, and so we can just compute them by computing cohomology groups, Dolbeault cohomology groups. So the whole game becomes to find, if you want to build models of particle physics, the whole game boils down to the following: you have to find pairs Z, V, where Z is your Calabi-Yau threefold, and V is a Hermitian Yang-Mills bundle of the appropriate rank, such that the degree 0 Dolbeault cohomology group, which is the thing that computes the infinitesimal symmetries of the bundle, this has to produce your 4-dimensional gauge group, SU3 times SU2 times U1. And the matter, which the infinitesimal deformations of this bundle, they're computed by the degree 1 Dolbeault cohomology groups. They have to give you 3 generations of matter plus the Higgses. And then we also want to know various other things. We want to know interactions. So a simple one is the Yukawa couplings. So they can be identified with the triple Uneda pairing, triple Uneda product, which is a singlet on a Calabi-Yau threefold. Can it be identified with a singlet on a Calabi-Yau threefold? And of course, you want the various phenomenal constraints of that. But anyhow, these are quantities you can compute at the level of cohomology. Okay, so that's a well-known story, and I've reviewed it. Now, in the year 2011, I also have to give a quick discussion of the landscape. So, of course, in '85, there was maybe a handful of Calabi-Yaus and even fewer bundles, Hermitian Mills bundles that we could put on it. By now, that's rather exploded, and in particular, I'd like to just briefly recall that there's this argument of Deneuve and Douglas, who gave a rough count of the number of vacua in F-theory models, but their arguments actually go through word for word in some classes of heterotic models, the ones I was just talking about. In context of the heterotic string, you want to know, okay, we have these Hermitian Yang-Mills equations, we have a Calabi-Yau, so can we count the number of solutions to the Hermitian Yang-Mills equations? And we can give a rough estimate for it, and it's basically it's a very rough count. The number of vacua is given by lambda, which is some kind of cutoff on which comes from tuple. Okay, there has to be some cutoff, which has to do with tuple cancellation. And you raise that to the power Betty, where Betty is the rank of some flux lattice. Again, this was done in F-theory, but it also works for the heterotic string. And now, in a typical visible sector of a heterotic model, at least for the case I have in mind in particular is just bundles on an elliptically fibered Calabi-Yau. This number Betty is around 10 to the 3 or so. And even with very conservative cutoff lambda of order 10, that tells me that the number of vacua, as a first guess, is around the number of 10 to the 1,000. Okay, so these are, of course, gigantic numbers. You don't want to, there's no point trying to enumerate them, put them on a computer or anything like that. But in particular, if your goal is to find the vacuum which represents our world, the standard model, I mean, from this point of view, that's virtually hopeless. But on the other hand, these numbers are, I mean, from this, it should be clear that these models are essentially all the same. All I've done here is I've taken a rank 5 bundle. All these models are going to give me an SU5 cut group in 5 dimensions with n generations of matter. I didn't put on, I still have to put a cut on number of generations, but anyhow, these models essentially all look the same. Okay, so you have gigantic numbers, but I think what it really justifies is the fact that is this idea of naturalness. So you have a model, it has certain parameters, and the fact that you have this enormous landscape essentially tells you that you should take all your dimensionless parameters to be of order 1, unless there's extra structure, like extra symmetries or something like that. So that doesn't mean that the landscape is still large, but these enormous numbers that you get is somewhat misleading. Okay, now, so I've reviewed this basic story of the heterotic string in 10 dimensions, and there's one important fact that I forgot to say is that the thing that made this, the thing that made it work in some sense, that got you these nice gut models, was the fact that you used an exceptional symmetry. I didn't really explain how that came about, but if you look closer at these models, the thing that really made them work was the fact that you had this exceptional gate symmetry. Okay, and as I've reviewed, essentially all we've done is we've taken 10-dimensional supersymmetric Emil theory with a exceptional gate symmetry in E8 gates group, and we've compactified that down to 4 dimensions. So now you might as well ask, okay, so we have supersymmetric Emil theory in 10 dimensions, but we also have supersymmetric Emil theory in d smaller than 10 dimensions, so why don't we just compactify those with an exceptional gates group, and that should also give models of particle physics. And perhaps in 85 the objection would have been that, well, we don't know any examples of how supersymmetric Emil theory with exceptional gates group is realized in string theory. But by now, there was in the 90s there was a duality revolution, and then we realized that we could get them in any dimension. So in particular, in M theory, if you compactify M theory in an exceptional ALE space, you get exceptional 7-dimensional supersymmetric Emil theory. If you compactify F theory on a ALE space, you get 8-dimensional supersymmetric Emil theory E8 gates group. And also in 9 dimensions, there was work by Pociński and Witten, which showed that in the strong coupling limit of type 1 prime theory, you could also get exceptional gates groups. And this time they live in 9 dimensions. Okay. So in principle, you can take all these supersymmetric Emil theory and start compactifying them, and you should be able to build models of particle physics just like we did for the heterotic string. Okay. At this point, since the mid-90s, there's basically no excuse not to do this. And so the story is essentially pretty much parallel to what I've just explained to you for the heterotic string. So in the heterotic string, the main ingredient was this this bundle V. This Hermitian Emil's bundle V, which we had to compactify in an internal Calabi-Yau. And the main thing that's going to change is that instead of a bundle V, we're going to need a Higgs bundle. Okay. So what's a Higgs bundle? Well, the basic point is that the maximalist supersymmetric Yang-Mills theories are all obtained from the 10-dimensional supersymmetric Yang-Mills theory by dimensional reduction. Okay, dimensional reduction basically means that you take some components of the gauge field and you take some invariance under shift symmetry in the 10 minus d dimensions, and that effectively turns your gauge fields into Higgs fields. And so when you compactify supersymmetric Yang-Mills theory, the data for bosonic field is going to be, well, there's still a gauge field, so you're going to need some bundle E, the connection A mu. And now, because it's dimensionally reduced supersymmetric 10-dimensional Yang-Mills theory, you also have this Higgs field. And this Higgs field, you should think of it as a map from E to E tensor n, where n is some twisting bundle, and the precise bundle that you need depends on the dimension that you're in. Okay. And further, we want to preserve n equals 1 super-Poincare covariance in 4 dimensions. That means that this data, phi and a, has to satisfy some first-order BPS equations, and they're essentially Hitchins equations. Okay. So this is the analog of the heterotic story. So instead of a bundle, which is Hermitian Yang-Mills, we get a Higgs bundle satisfies Hitchins equations. Okay, so let's go through this in the F-theory story. So what was F-theory again? So F-theory, from my point of view, is essentially 8-dimensional supersymmetric Yang-Mills theory with an exceptional gauge group. Okay, so we had this, in even dimensions, I can always use complex geometry, so I've already used this to split up things into holomorphic and to holomorphic type. So we had this 10-dimensional gauge field, which by dimensional reduction to 8 dimensions, it becomes this 8-dimensional gauge field, and I've really only written the internal part. So 8 dimensions has to be compactified on a 4-dimensional manifold, and this is the part along the 4-dimensional manifold. And this is the 2 scalars that you get from dimensional reduction. I've combined them in a complex scalar. Okay. Now we had 8-dimensional supersymmetric Yang-Mills theory. We want to compactify this down to 4 dimensions. Okay, so I take a Cayley surface S. It's actually slightly over-restrictive. I could do with less structure, but okay, let's just take it to be Caylor. And now I have I put an E8 bundle V on that with the connection. So A01 is supposed to be the connection on this bundle V. And then we had a Higgs field phi, which is going to be a map from V to V tensor K. Okay, so it turns out that you need the canonical bundle of this surface S to preserve n equals 1 supersymmetry, 4 dimensions. Okay, so we define this little 2-step complex, which is E dot. And then the Hermitian Yang-Mills equations, by dimensional reduction, reduce to Hitchins equations. So these are Hitchins equations for the system. And again, just as for the heterotic string, I needed to compute some Debye homology groups in order to find the 4-dimensional gauge group and the 4-dimensional matter. It's exactly the same here. You have these hypercohomology groups of this little complex. The degree 0 hypercohomology groups computes the infinitesimal symmetries. So that's supposed to be SU3 times SU2 times U1. And the degree 1 hypercohomology group of this complex computes the infinitesimal deformations of the Higgs bundle. So that has to you have to require that to give you the matter, the 10, the 5 bar, and the Higgses. And of course, there's a triple product on this thing, which gives you the native pair, which gives you the superpotential, Yukawa couplings, and so on. Okay, so this is the game you have to play. You pick a surface S, you pick a Higgs bundle on it, and then you try to find configurations for which the Debye homology groups give you the standard model, or a gut extension of it. And and then you can play with it and try to do phenomenology. Okay, just briefly, and so it's a similar story in 7 dimensions and 9 dimensions. So dimensional reduction of 10 down to 7 dimensions, or Hermitian Yang-Mills equations from 6 down to 3 dimensions, effectively, because we always assume 4-dimensional Poincare variance. Okay, it gives you the real version of Hitchins equations in this case. And so you want to construct real Higgs bundles on a real compact 3-manifold. And 9 dimensions, dimensional reduction of Hermitian Yang-Mills from 6 down to 5 dimensions gives you a generalization of the Bogomolny equations. This is very similar to the Bogomolny equations for monopoles. Okay, so those are the equations you have to satisfy. Then you want to construct solutions. And here it really matters which dimension you're in. And the F-theory case, a-dimensional case, is the maximally simplest case for a number of reasons. So I'll focus on that because I can present it in a very simple way. So we want to construct solutions to these equations that we wrote over here, compactified on a Kähler surface S. Let's just stick to be a Del Pezzo surface, something like that. Okay, so we want to construct these Higgs bundles, canonically twisted Higgs bundles on this complex surface S. Now, there's a very standard way to do this, which has been around at least since Hitchin's paper from 1987. You split it, the equations that I wrote, they're split in two types of equations. They're split into complex equations, actually two complex equations. F02 is 0, which you want a holomorphic bundle on S. And del bar phi is 0, which means that phi is holomorphic. And a second type of equation, which can be interpreted as a moment map equation, Fij bar Gij bar plus phi star phi is equal to 0. And so the basic idea is you first construct solutions to that, basically ignoring this. And then once you've constructed solutions to this, you try to prove a theorem that says that given a solution to this under nice conditions, there exists a unique solution to this equation. Okay, so that's of course a standard strategy, and it's particularly simple. Well, modulo one issue, which I skip over, but it's particularly simple in this case because my Higgs bundle takes values in a line bundle, and that effectively abelianizes the problem for you. So again, so we want this bundle E, and we want this Higgs field phi, and we originally started with an unbroken E8 gauge group in 8 dimensions. If you want to break that to SU5, again, it's a standard story. In the heterotic string, you would turn on an SU5 bundle. And in this context, you would turn on an SL5C Higgs bundle on S. Okay, so what we really need to do is construct the SL5C Higgs bundle on S. Okay, well, that's very simple. You can use what's called the Higgs bundle spectral cover correspondence to turn constructing Higgs bundles into constructing it's called a spectral sheaf. Basically, you construct the eigenvectors and you construct the eigenvalues. So that's the abelianization. And the spectral cover for SL5C Higgs bundle is simply a degree 5 covering of the base. And so you can explicitly write this down by writing down a degree 5 polynomial, complex polynomials. This is very simple, and it's effectively it's a divisor inside the canonical bundle over S. So that's why it's so simple, because divisors are simple. And additionally, I need a spectral sheaf. So I need a sheaf, or in nice cases, a line bundle on this divisor. So that's a generator of the Picard group of C with some extra restriction, but again, I won't go into it. And well, this is in some sense where the landscape comes in that I showed you earlier, the 10 to the 1,000 solutions. So I can't write them all down, but I can easily write some very simple classes of models, some very simple line bundles on this spectral cover, on the spectral surface. And therefore, I get just by doing that, I've solved the F terms for the system, and I get a 4-dimensional SU5 cup model. If only it were this easy for d equals 7 and d equals 9. That would be nice. Okay, then we need to solve the d terms, and the standard approach is then to use the Kobayashi-Hitchin correspondence, which essentially tells you that, okay, so what you want, first you reinterpret the d terms as saying that I want a certain special canonical metric on my bundle, which is usually called the Hermitian-Einstein metric. And the Kobayashi-Hitchin correspondence says that this Hermitian-Einstein metric exists if and only if the Higgs bundle, or the spectral sheaf equivalently, is polystable. So then you need to check polystability, and you're done. Okay. Now I've emphasized this idea of compactifying Yang-Mills theories. That's actually, if I briefly go back to this table, in some sense that's not quite how it's embedded in type 1 prime F theory and M theory. The usual definitions of F theory, M theory, and type 1 prime, they involve geometries which develop ALE singularities. And these ALE singularities, the physics of these ALE singularities is then interpreted in terms of Gates theory. So if you really want to embed it in a string theory, there's one additional step you want to do is you want to map it to some kind of space with ALE singularities. Okay. And that additional step, again, there's a correspondence that we can use, is the Higgs bundle ALE vibration correspondence. And okay, this is not quite the version that I need, but I try to slightly oversimplify things a little bit. Thank you. Okay, so I'm going to gloss over some things and oversimplify a little bit. But okay, so let's consider SLNC Higgs bundle on this complex surface S. And suppose that I want to construct an AN-1 type ALE vibration over S. Okay. So this is an equation of ALE. It's 3 variables, so it's a 2 complex dimensional space. And this sits over S. So the whole thing in this case is 8 real dimensional or 4 complex dimensional manifold. Okay, this Y is 4 complex dimensions, 2 complex dimensions of the ALE, and the base is S. Okay. Now, okay, there's n lines in this surface, which I can write the equations as y equals x and b0 z to the n plus dot 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 plus bn equals 0. Okay, this is degree n, so this is n solutions, and you can then think of these lines as being parameterized by y or by x. Okay. So I construct an object which is called the cylinder, which consists of these n lines varying over S. Okay, and then I have 2 natural maps. First of all, the lines, of course, are naturally embedded in this ALE vibration. There's a map I from R into Y, and then secondly, this guy over here, this can be interpreted as a degree n equation in the canonical bundle over S, and therefore gives me a degree 5 covering over S. So that's my spectral cover C. And so I also have a map from R to C, which essentially maps each line to a point inside in the fiber over S. Okay, so I have these 2 maps, and now there's a correspondence which tells you that the cohomology, this correspondence is actually holomorphic. So I should really write PQ type and not just star. So the cohomology of C gets mapped to a certain subclass of the cohomology of Y up to a shift by +2 by these 2 maps, pi star, I star, and I lower star, B star. So you can map between these things. And this map's holomorphic. And so the idea is that given a Higgs bundle, I can construct an ALE vibration, which in this case, it's 4 complex dimensional manifold over S. And if you've heard about F theory being elliptically fibered Calabi-Yau fourfolds with G fluxes and so on, okay, so this Y is my elliptically fibered Calabi-Yau fourfold. So that's how you reconstruct that. But I have to say that if you think about it in terms of Calabi-Yau fourfolds and so on, I don't know, it's a huge amount of confusion I see in the literature. But I would say that for many purposes, it's much clearer if you think about the Higgs bundle picture or the spectral cover picture. Much less likely to get confused. Okay, so there's analogous stories, although they're much less understood. In principle, there are analogous stories for the other cases. So I mentioned, for instance, the other case that I sort of understand. It's a 7-dimensional case. So the usual story that you hear is that particle physics is an M theory is supposed to come from M theory compactified on a manifold of G2 holonomy. Okay, so where do we get this G2 holonomy manifold from? I didn't tell you anything about G2 holonomy. I just told you about 7-dimensional Gates theory and Hitchins equations. So the idea is just like I constructed the Calabi-Yau fourfold from the Higgs bundle and from the real Higgs bond over a free manifold, I can construct a 7 manifold, which is a Leaf vibration over my real free manifold, and that's supposed to have G2 holonomy and ALE singularities. And in type 1 prime, again, there should be a similar story, except it's even less understood. Okay, maybe that would be for another day. Okay, so here's the executive summary of the talk. So basically, getting particle physics from strings. Okay, it's not quite an implication, but huge classes of very interesting models can be constructed by thinking of compactifying supersymmetric Mills theory in various dimensions, down to 4 dimensions. And compactifying supersymmetric Mills theory in a way that preserves supersymmetry is an exercise in constructing Higgs bundles. Okay, so that's the main idea. Okay, so then I have some questions for mathematicians, ideas that I have had trouble trying to solve. So as I've emphasized in even dimensions, 8 dimensions, particularly, we have a pretty good idea how things work because we use complex geometry and because I can talk to Ron. And but in odd dimensions, it's a different story. Morally, it's the A model-like. So it's symplectic geometry and Lagrangian manifolds and all this stuff. And it's much, much harder to construct these things. And I have much more limited results in these contexts. So for instance, for this story of 7-dimensional Young-Mills theory, if I want to compactify that, what I'm essentially supposed to do is I'm supposed to construct Lagrangian coverings, Lagrangian manifolds inside the cotangent of my free manifold. And I can only construct some very simple classes. I don't know how to construct a generic solution. And in 9 dimensions, in some sense, it's even worse. So the problem I would pose is, okay, we know Hitchens equations, and now how do I construct solutions, the generic solution to this for real Higgs bundles or for these 5-dimensional versions of Higgs bundles, these Bogomolny-like equations that I don't know how to do. Trying this with Tony Pantev, and okay, we had some ideas, but I'm not sure we had the right idea, but anyhow, this is one idea for trying to turn this problem into an algebro-geometric problem. There's, of course, once you construct, so this is the complex part of Hitchens equations. That's a spectral cover construction, essentially. Once you've done that, you need some analog with the Kobayashi-Hitchin correspondence. I have to say that even in the 8-dimensional case, I've been lying to you a little bit because the usual form of the Kobayashi-Hitchin correspondence applies to ordinary Higgs bundles. The Higgs bundles that we were interested in, even 8 dimensions, actually are mirromorphic Higgs bundles, so they have some singularities. And mirromorphic Higgs bundles, the Kobayashi-Hitchin correspondence is pretty well understood for Riemann surfaces, by work of Simpson and others. It's much less understood in higher dimensions. So even in the models that I showed you, strictly speaking, I mean, it's expected to be because this tends to be pretty robust, but strictly speaking, I don't actually know that I can solve the Hermitian-Einstein metric in these models. So it'd be nice to sort that out. And also, I'm very confused about the notion of stability for A-branes. I'm not sure that I understand what the correct condition is for stability for A-branes. Particularly at a recent paper with Ron, where we run into some issues with intersecting Lagrangians, and then I realized that even in type 2A string theory, it's not really understood what the correct stability condition is for A-branes. Okay, there's an interesting conceptual question. So I've emphasized this point of view to you that there's a priori answer. The 4-dimensional Gates group is computed by some kind of H0, so kind of degree 0 cohomology group of your Higgs bundle. And the 4-dimensional matter content is computed by degree 1 cohomology group of your Higgs bundle. You can also state this in terms of the spectral cover. In spectral cover, you're supposed to compute X groups in even dimensions, or some kind of Fleur cohomology groups in odd dimensions. But what about this ALE fibration picture? What is actually the a priori answer? So I have this structure of ALE fibration and some kind of gerb on it. How do I actually classify the deformations, first order deformations of this structure? I don't actually know. And you should remind here that these solutions are singular. If it were smooth, then it's not that hard, but these are singular things. I don't know the a priori answer for what classifies as first order deformations in terms of these ALE pictures. And there's the ALE pictures in some sense, if it were just the ALE pictures, this wouldn't be all that important because I can map it to a problem in gauge theory where I do know how to solve it. But in the end, you want to also embed this back into a global model. You want to compactify this local model. And if you don't know the, in that context, we certainly also don't know how to classify first order deformations when you have the singularities. So a good place to start understanding this would be in a local model. And then there's another thing that I've been puzzled about is these 5D versions of Higgs bundles. The spectral cover corresponds to some kind of coisotropic brane. But the equations that we have for it look, so there's another type of coisotropic brane that's been in the literature, the Kapustin-Orlov type coisotropic brane. And while they're both coisotropic, the equations for them actually look rather different. In particular, the equations I wrote are actually, where are they? Well, they're non-abelian. And so that's already the first difference with Kapustin-Orlov, where they only have abelian branes. And I'm very confused about the fact that there seem to be these two kinds of branes. And somehow you think they'd be the same, but I'd like to know what's the relation between them, or if there should be a relation between them at all. OK, so that's essentially summary and the questions I had for mathematicians. So I think I'll stop there. That's right. No, yeah. So, so it's clear. So you have the spectral sheaf. It has two pieces in some sense. There's its support, and there's the gauge field on it. So the support gets mapped to the geometry of the ALE fibration. So that's pure geometry, and the gauge field of that spectral sheaf, it gets mapped to well, depending on the context, it's a tensor form usually. So if you're doing this in the context of F theory has this free-form field, which has this four-form flux. You write this G4 equals D of C3. So the point is that the line bundle, the gauge field on the line bundle gets mapped to C3 in F theory in that picture. No. No, but the holomorphic data. So it's not true that the Hermitian-Einstein metric can in fact not be mapped to the ALE fibration, but the holomorphic data can. So the holomorphic data can be abelianized. That's this idea of this Higgs spectral correspondence. Anti-self-dual instanton with what? With zero Higgs field? What's the... Yeah, I don't know. That's a very degenerate case. No, it's very degenerate from the point of view of the Hitchens system. Because phi is identically 0. In fact, you wouldn't be able. In fact, that wouldn't even be a solution in my context because, as I said, you need singularities. You need the Higgs field is meromorphic, so it actually has to be non-zero in some sense. I'm sorry? The Higgs field has to have. The Higgs field has to have singularities. Yeah. Sources. Otherwise, you don't get anything. It's the analog of saying that it's an analog of the flavor brains. This is how you get matter in these models. You have to have flavor brains. That's the singularities of the Higgs field. In a sense. Okay, that's not quite right, but that's why you have to have something non-compact, morally speaking.
In that language, by restricting yourself to an E8 bundle, or in constructing things in E8 language like this, are you restricting yourself to the case where those flavor brains are in the same homology class as, in other words, these things are continuously connected to like an unbroken E8 field?
It's not continuously connected precisely because you have these non-compact. So the 8 is always broken. I cannot continuously connect it.